Lower bounds. Now that we have seen that there exists an auction that has constant competitive ratio to F2, it is interesting to ask, what is the optimal auction in terms of a worst-case competitive ratio to F2? What is the competitive ratio of this optimal auction? In this section, we approach this question from the other side by looking for lower bounds on the competitive ratio. Specifically, we discuss a proof that shows that no auction is better than 2.42 competitive. Theorem 13.37. No auction has competitive ratio less than 2.42. The proof of this theorem involves a fairly complicated analysis of the expected value of f2 of b, where b is generated from a particular probability distribution. We will instead prove a simpler result which highlights the main ideas of the theorem. Lemma 13.38. No two-bidder auction has competitive ratio less than 2. Proof. The proof follows a simple structure that is useful for proving lower bounds for this type of problem. First, we consider bids drawn from a particular distribution. Second, we argue that for any auction A, EB of A of B is less than or equals to EB of F2 of B over 2 divided by 2. This implies that there exists a bit vector B star such that A of B star is less than or equals to F2 of B star divided by 2. We choose a distribution to make the analysis of EB of A of B simple. This is important because we have to analyze it for all auctions A. The idea is to choose the distribution for B so that all auctions obtain the same expected profit. Consider B with Bi satisfying probability of Bi greater than Z equals to 1 over Z. Note that whatever the price Ti is that A offers, bidder I, the expected payment made by bidder I is Ti times the probability of Bi, which is greater than or equals to Ti, which is equals to 1. Thus, for n equals to 2 bidders, the expected profit of any truthful auction is EB of A of B equals to n equals to 2. We must now calculate EB of F2 of B. F2 of B equals to the maxima of I times Bi, where I is greater than or equals to 2, and where Bi is the highest bid value. In the case that n equals to 2, this simplifies to F2 of B equals to 2 times B2 equals to 2 times the minima chosen between either B1 or B2. We recall that a non-negative random variable x has expected value of x equals to the integrations of the probability of x which is greater than or equals to z dz, integrating starting from z equals to 0 to z equals to infinity, and calculate the probability that f2 of b which is greater than z. Okay, the following is the calculation. The probability b of f2 of b greater than z equals to the probability b of b1 is greater than or equals to z over 2 and b2 is greater than or equals to z over 2, which is equals to the probability b of b1 is greater than or equals to z over 2 times the probability of b2, which is greater than or equals to z over 2, which by combining both the multiplications of both probabilities equals to 4 over z squared. Note that this equation is valid only for z, which is greater than or equals to 2. And of course, for z is less than 2, the probability of f2 of b greater than or equals to z is equals to 1. Thus, EB of f2 of b equals to the integration of the probability of f2b, which is greater than or equals to z dz, integrating starting from z equals to 0 to z equals to infinity, will be equals to 2 plus the integrations of 4 over z squared dz, integrating starting from z equals to 2 to z equals to infinity. And the results will be 2 plus 2 equals to 4. For this distribution and any auction A, EB of A of B equals to 2, and the EB of F2 of B equals to 4. Thus, the inequality EB of A of B is less than or equals to EB of F2 of B divided by 2 holds, and there must exist some input B star such that A of B star is less than or equals to F2 of B star divided by 2. For two bidders, this lower bound is tight. Indeed, it is trivial to check that for two bidders, the Vickrey auction has competitive ratio 2. The lower bound proof given above can be generalized by a more complicated analysis to larger n. Such an analysis leads to bounds of 13/6 for n equals to 3 and eventually to a bound of 2.42 for general n. It is conjectured that these bounds are tight. Indeed, they are tight for n which is less than or equals to 3.